All right, this is question 1.50. It's one of the practice problems from chapter 1. And the question just asks us to predict the expected hybridization state and geometry for the central atom in each of these compounds. Well, here we have a nitrogen that's got 3 sigma bonds and 1 lone pair. So it's got a steric number that's equal to 4. Therefore, it's sp3 hybridized, right? If we think about the electron configuration of nitrogen, it's 1s2, 2s2, and then we have 2p, 1, 2, 3. So if we look at the valence electrons, we have the 2s orbital, we have 3 degenerate 2p orbitals, we have 1, 2, and then 1, 2, 3 unpaired electrons in the 2p orbitals. Okay, it looks good here. Like we have a pair of electrons, like we have a lone pair in the molecule, and then 3 unpaired electrons to form the 3 sigma bonds. However, since it's sp3 hybridized, we have to hybridize all of those orbitals so that we have 1, 2, 3, 4 hybrid sp3 orbitals, and we still have a total of 1, 2, 3, 4, 5 electrons in those sp3 orbitals. And so this orbital here represents the lone pair, and then these 3 over here represent the 3 sigma bonds. So if we have a steric number of 4, sp3 hybridization, those 4 sp3 hybrid orbitals are going to seek to get as far away from each other as possible. And so my central atom, my nitrogen, is going to have the lone pair. I'm going to draw in an orbital just because. We have 1 hydrogen in the plane, we have 1 hydrogen coming in back, and then we have another hydrogen coming out in front like this. Now, molecular geometry considers bonds only, right? It doesn't consider the lone pair. And so the molecular geometry here would be trigonal, pyramidal. Trigonal, pyramidal. All right, let's take a look at the next one. It's BH3. If we look at the steric number, we have 3 sigma bonds, no lone pairs. So the steric number is 3. Therefore, this boron is sp2 hybridized. If you look at the electron configuration for boron, it's 1s2, 2s2, 2p1. So if we look at the valence electrons, you've got a 2s orbital. You've got 3 2p orbitals like that. You've got 1, 2 electrons in here and 1 in here. But that doesn't make sense because we've got 3 sigma bonds, so we need to have 3 unpaired electrons. What does that mean? It means I'm going to take one of these electrons and I'm going to put it into a p orbital. Therefore, we're going to have to hybridize only 3 of these orbitals. And when we do that, we get 3 hybrid sp2 orbitals. Each one has 1 electron in it. And then we also have the leftover 2p orbital, which has nothing in it. It's an empty 2p orbital. And that's why boron can act as a Lewis acid. It can act as an electron acceptor. If we think about the molecular geometry, if it's sp2 hybridized, all 3 of those sp2 orbitals are going to try to get as far away from each other as possible. So they're going to adopt a trigonal planar geometry. So this molecule will be trigonal planar. Let's move on and take a look at a methyl carbocation. So if we have CH4, so this is C. CH4 is methane, so if you have CH3, it's called a methyl. Anyhow, this is a methyl carbocation. Well, we have 3 sigma bonds, and we have no lone pairs. We have a steric number that is 3, therefore its hybridization is sp2. Carbon is 1s2, 2s2, 2p2. If we look at the valence electrons, we have 1 2s orbital, we have 3 2p's, we have 1, 2, 3, 4 total electrons. But we lost an electron, didn't we? Because we've got a carbocation. So we're going to erase one of those electrons, and we're going to erase one here. It's actually 2p1. So then what do we need to do? Since we need to have 3 sigma bonds, we're going to take this electron and we're going to move it into one of these orbitals. Therefore, we need to hybridize 3 orbitals, and we make 3 hybrid sp2 orbitals like this. Now we've got 1, 2, 3 unpaired electrons, and we've got an empty 2p orbital, right? So if we have 3 hybrid sp2 orbitals, again, all 3 of those bonds or those orbitals are going to distance from each other as much as possible in the carbocation, and therefore it's going to be trigonal trigonal planar. And the last one is a methyl carbanion. So let's do that here. So, oops, this is D, not B. So we have a methyl carbanion like this. Okay. We have the negative charge here. Our steric number is equal to 4. We got 3 bonds and 1 lone pair. Therefore, it's sp3 hybridized, right? If we look at carbon, it's 1s2, 2s2, 2p2. But since we have a negative charge, we're going to add an electron. So it's 2p3. So we draw our 2s orbital. It's got 2 electrons. We draw our 3p orbitals, 2p. We've got 1, 2, 3 in there. It might look good to say, okay, well, there's my lone pair. There are my 3 sigma bonds. But again, since it's sp3 hybridized, we have to hybridize all of those orbitals. So we end up with 1, 2, 3, 4 degenerate sp3 orbitals. We have 1, 2, 3, 4, 5 electrons. These 2 represent the lone pair. These 3 represent the sigma bonds. And so if those 4 sp3 orbitals want to distance themselves from each other as far as possible, I'll put the lone pair in here just for fun. I'll put the negative charge. Actually, I should put it by the carbon. But anyhow, we're going to have 1 hydrogen in front. We'll have 1 going in back like this. And so our molecular geometry, which again only considers the bonds, which are these bonds here, our molecular geometry will be trigonal pyramidal. Trigonal pyramidal, like that. All right, that's question 1.50. I also wanted to take a look at question 1.59. Let me just find it here. It says, it shows you the structure of the molecule caffeine. Every once in a while I have a student that will have a t-shirt that has the structure of caffeine on it. So let me draw it the way that they have it here. So it's not drawn as a bond line structure because this is chapter 1, and I'm sure you could all draw it as a bond line structure now, probably very quickly. So let me just get this done here. So we have these 3 hydrogens over here. We have another CH3 group down here. We have this nitrogen in this ring here. Another one here, like that. I find it harder to draw a molecule as a Lewis structure than as a condensed structure, or sorry, as a bond line structure. Anyhow, it says, here's the structure of caffeine, but they've left out all of the lone pairs. So where am I going to put in lone pairs in this molecule? Well, there's no carbons that have a positive or negative charge. So if I have a carbon with a negative charge, I would put a lone pair on those. But just to put this bug in your ear, all oxygens and nitrogens should have lone pairs on them, shouldn't they? Yes, absolutely. So on all nitrogens, we need lone pairs because nitrogen is trivalent. It always forms 3 bonds and has 1 lone pair. So on all of my nitrogens, I have to put a lone pair on each one of them. And my oxygen always has, I can draw a better oxygen than that. Oxygen always has 2 bonds and 2 lone pairs. Exactly, Kelly. So on my oxygens, they all have 2 bonds. So this one and this one. And so there you go. I've covered all of my heteroatoms. So anything that's not a carbon or a nitrogen, and I have the lone pairs on all the nitrogens, and I have the lone pairs on the oxygens. There you go. Doesn't take too long to solve that one there. Put all the lone pairs in the caffeine molecule. Again, drawing a structure without lone pairs, there's nothing wrong with doing that. But an organic chemist has to know where the lone pairs are. So question 1.61, since we've already covered bond line structures, I'm going to draw all of these compounds as bond line structures. So we have a couple of chlorines here, then in B, meta. So here we go. This is B. C is this molecule. We have a chlorine here and a chlorine here. And then D, we have a chlorine and a bromine that are paired to each other. There we go. So the question asks, identify which compounds possess a molecular dipole moment and indicate the direction of that dipole moment. Are there any compounds in here that people think might be polar compounds?
C.
C. So C would be a nonpolar compound. In C, we have two dipoles, right? We have a dipole between the carbon and chlorine, okay? Because if you have a carbon-chlorine bond, carbon has an electronegativity of 2.5, and chlorine has an electronegativity of 3.0. Therefore, a dipole is always going to go in this direction. However, here they cancel, don't they? Yes, yes, Bruna's correct. Yeah, she says they cancel. Absolutely. If you look at A, let's go up to A, we have a dipole going this way and a dipole going this way. And I see several students have said that's a polar molecule. They're 100% correct, because if you take these two vectors and you tally them up, you know, tip to tail like that, oops, how do I do it? There we go. You end up with a resultant vector that is going off, you know, in this, son of a gun, in this direction, like this, right? If you tally them up, you'll end up with a vector that's going in that direction. So overall, the molecule is polar. See if I can fix this back like that. Okay, for the same reason, B is a polar compound, right? So B is a polar compound. We have a dipole going this way and a dipole going that way. If you tally up those dipoles, you're going to get a resultant dipole like this. And if you look at D, well, there's going to be a slight dipole in D. This is a question that one of my students asked me the other day. It's because they said, well, if you look at carbon-bromine bond, according to the rules in our book, you know, the carbon-bromine bond is considered nonpolar. It would have a slight dipole. But either way, you're going to have a dipole going off in this direction, right? From the carbon towards the chlorine. Even if there was a slight dipole here, it's going to be much smaller. And so overall, the resultant dipole will be in this direction. So somebody says something about ionic. So there's no way that any of these compounds could be ionic, okay? So an ionic compound is when we have a metal and a non-metal, right? A metal and a non-metal. And there's no metals in here, right? Sodium chloride would be an ionic compound because sodium is a metal. All right, there we go. So we have three polar compounds, and then we have one non-polar compound, the one that I have circled in green. Something else that I'll teach you really quickly here is when you have two, and if you're going off charge difference, there's no way it could be ionic, right? The only way that you can have an ionic bond is when you have a difference in electronegativity that is greater than 1.7, according to our textbook, right? And since every element that you see in here comes from the P block, there's no way that you could have a difference of more than 1.7. Again, you'd have to combine a metal with a non-metal in order to have an ionic bond. So if you have an aromatic ring like this and you have two groups on an aromatic ring, maybe I'll do this over here. If you have two groups on an aromatic ring, okay, and this only works for di-substituted aromatic rings, meaning aromatic rings that have two things attached to them. So let me show you something quickly here. If I draw three aromatic rings, if you have two substituents on an aromatic ring, let's say you have one that's X and the other one's Y. Well, there's three ways that you could organize them. You could either have them like this, you could have them like this, or you could have them like this. All three of these compounds are isomers of each other, but you can see how there are three distinct ways of organizing them. If you number them, this, you know, if you count the X is number 1 each time, this one is going from 1 to 2, this one is from 1 to 3, and this one's from 1 to 4, like that. So you could call this 1-2 substitution, this one 1-3, and this one 1-4 substitution. But you can imagine that organic chemists have to have a better way of doing it than that. And there's a really old system of nomenclature that we use in aromatic compounds. And if you're the kind of person that likes to, you know, look at this, you know, Google everything that we ever do in class, you could look this up to see. But when you have two substituents on an aromatic ring and they're next to each other, we say that they're ortho substituted. When they're 1-3 substituted, we say it's meta. And when they're 1-4 substituted, we say that they're para substituted. So ortho, meta, para. Again, these are things that you will learn in organic chemistry too. However, you see so many di-substituted aromatic compounds in organic chemistry 1 that I always kind of go over it quickly with my students. And you know what? Some of them have even learned it in general chemistry too. When you do a little chapter on organic chemistry, some of my students already know that coming into class, okay? Or coming into organic chemistry 1. So something kind of interesting there. All right.